Hello everyone, welcome to lecture 9 of this course on diffusion models. I am Dheeraj Madan and today we will be learning about stochastic differential equations for generative modeling. So we have already seen diffusion models. We have also seen score based models, and in a sense both of these consist of discrete number of time steps. Both of these use a discrete number of time steps in order to sample a point from the data. So we have seen diffusion models, we have seen noisy conditional score networks, right? So both of these are based on discrete time steps. Both of these use discrete time steps for sampling from data distribution. So the question now is that can we sample from a continuous number of time steps, right? So can we extend the sampling? For continuous time steps. Okay. So in order to formalize the notion of continuous time steps, we'll introduce the idea of something called as stochastic differential equations. So this was introduced in the paper titled Score-Based Generative Modeling through SDE. So this is the paper. This paper is by Song et al. Okay, so the link to this paper is given in the description box below. So before we study, stochastic differential equations, we'll have to understand some basics of stochastic processes and Brownian motion. So let's see that. So what is a stochastic process? Okay. So a stochastic process is a collection of random variables which are indexed by this time. Okay, so defined on a common probability space. Omega fp. So as you might be knowing, so here omega is essentially the sample space, f is sigma algebra. So it's a collection of sets which are closed under unions, intersections, complements, and it contains empty set in the full set. And this is a probability distribution, right? So basically, to every element on this set in F, it assigns a probability value, and probability of the entire set is 1. This is a probability function. Okay. So here what it means is that, so since each of these is each of these xt is a random variable, so therefore for all t we have that xt is essentially a function from omega to r, okay, such that xt inverse minus infinity to x. Okay, so that belongs to f for all x in R, right? So here T is called as the parameter space or the time space. So T is called as the parameter space. Okay, you can also call it the time space. Okay, and the range of xt. Okay, so the union over all t, the range of xt. This is called as so this is called as a state space. So let me write these down again. So essentially we have t or the time slash parameter space. So we'll give some examples as well, and the range of xt. Okay, so the range of this sort of xt, so this is called as the state space. Okay, and depending on whether this time space and state space, whether they are continuous or discrete, we can have different types of stochastic processes. So let's take some examples. Okay, so examples. So let xt, so we use it to denote the temperature at time t. Or it could even be, for example, the stock price at time t. Okay, so here we see that so time is also continuous, and temperature or the stock price, this is also continuous, right? So here this is a continuous time, continuous state space stochastic processes. Continuous time, continuous space stochastic process. So another example could be, for example, xt, let it denote the number of people waiting in a queue at time t. So we see that the range of xt here is discrete. So this is a discrete space, continuous time, stochastic process. So I'll encourage you to think about more examples for continuous space, continuous time, continuous space, discrete time, continuous time, discrete space, and discrete time, discrete space. So think of examples for all these four combinations. So take it as the homework exercise. So but let's proceed on. Let's now discuss a special case of a stochastic process, which is called as the Brownian motion. Okay, so Brownian motion is a continuous time and continuous state space stochastic process. Okay, so we'll denote it by Wt. So a stochastic process Wt t greater than equal to 0 is said to be a Brownian motion if 1. So firstly we have it starts from 0, so W0 is 0. Next, for all t greater than 0, Wt is continuous. So at every point it should be continuous. And thirdly, for all n with 0 less than equal to t0 less than t1 less than tn, the increments wti minus wti minus 1, so these are independent of each other. Okay, so basically wtn minus 1 is independent of wtn minus 1 minus wtn minus 2, which is independent of wtn minus 2 minus wtn minus 3. So all these are sort of pairwise independent of each other. And secondly, what we have is that, and in fact they are jointly also independent, so pairwise independent is a weaker condition, but essentially all these sort of the n increments, right, starting from wt1 minus w20 to wtn minus wtn minus 1, right, so all these n increments, they are all jointly independent of each other. And secondly, what we have, that this distribution of wti minus wti minus 1 is essentially normally distributed with mean 0 and variance ti minus 1. So the distribution is only dependent on the time difference, right? So it doesn't depend on the actual time. So here the special property is also called as stationary increments. We don't need to know that, but just for your sake I'm telling you, right? So basically third property is the one, you know, which completely defines the stochastic process. So let's see these again. So firstly, the stochastic process, right? So this starts from w0 equals to 0, okay, and then, you know, the trajectory is a continuous trajectory, okay. And thirdly, what we have is that the increments, right, so they are all independent of each other, and the distribution is given by a normal sort of distribution, right? So basically you start, let's take one sample trajectory. So basically you start from some point, and then, you know, at every time step, you know, think of it this way, that okay, there is some sort of a normal distribution going on. Let's you know, take some interval, let's say let delta t be a small interval, and let me discretize the time in units of delta t. Then the process will look like as follows, that, you know, I at every time step I sample some random variable normally distributed with, you know, mean 0 and variance delta t, and I, you know, I add to a cumulative sum. So this gives me, you know, some sort of cumulative process, right? It can go in positive or negative direction, and then, you know, it's a continuous process, but then it doesn't look differentiable, and well, actually it's not differentiable. So this is how, you know, it'll look like. So we can actually formalize this notion. So let's say how to sample a trajectory from Brownian motion. Right, so basically set t equals to 0, okay, and let delta t be some, you know, let me call it some floating point precision, or some precision I want, okay. So this is how we initialize, and w0 is of course set to 0. And let us say that, you know, I want to, let's say I want to run it for some time capital T. Then what I'm going to do is that for k in range 1 to t by delta t, okay, to w at k times delta t equals to w at k minus 1 times delta t plus some let's say some zk, right, where zk is normally distributed with mean 0 and variance delta t. So at every time I'll have to, you know, sample a fresh zk, and I add it to a cumulative sum. So this gives me, you know, one instance of a trajectory from this Brownian motion. And you see why, right? Because essentially we have to ensure that these properties are all satisfied. These three properties, right? So this continuity we have ensured, w0 0 we have ensured, and then essentially we have to ensure that these increments, they are independent and they are coming from this sort of distribution. So essentially this is not actual Brownian motion, because actual Brownian motion would have given me at every time step. Here it's kind of an approximation in the sense that we have discretized the trajectory, and then we have discretized the time, and then we are looking at how a discretized trajectory is going to look like, right? So coming back to the question, so can we redefine the diffusion models or score based models to work in continuous time? So let's revisit the denoising score model. So essentially recall what we do over here is that let x be my data and xi given x, I essentially add some sort of Gaussian noise to it coming from some variance sigma I square. Okay, and essentially we have a sequence of these variance terms wherein so essentially sigma 1 is greater than sigma 2 up to greater than sigma n, right? So essentially we learn sort of different models, so learn score models with each variance term. Learn score models for s theta x tilde comma sigma I, right? So basically this should essentially approximate gradient with respect to x tilde log of p sigma I of x tilde, right? So p sigma x tilde is essentially the distribution of x tilde which is obtained by sampling an x from my data distribution and then adding some noise which is a zero mean Gaussian noise with variance sigma I squared. So the distribution, so the score function of this, this xi is what is modeled by s theta x tilde sigma I. So this is how this model was defined. And how did we train it? Well, so the training procedure was that we essentially trained to minimize so we minimize over theta sum over I from 1 to n, okay, sigma I square, expectation of x from px, expectation of p sigma I from x tilde given x, and now we have the score function of x tilde sigma I minus gradient with respect to x tilde of log of p sigma I of x tilde given x. So this squared. So this is what we are minimizing, right? And the sigma I square, right? So remember, this is essentially a normalization constant in order to make each of these terms in order to make them independent, to make the magnitude independent of the sigma I. So that's why this has been added to it, right? Because each of these terms is order of 1 over sigma I, or the square is order of 1 over sigma I square. So by multiplying by sigma I square, it makes them of the same order, right? So this is how the training was done. Now how do we make these sigma I's in continuous time? So that's the question. So remember the sampling procedure for this, right? So the sampling procedure, we had, that consisted of sampling x. So sample. So essentially sample. Okay. So x I equals to 0 and m equals to I equals to 1, m equals to 0. So essentially I is the sort of the variance term. So initially we will be sampling from high variance, and then for as I goes from 1 to n, right, and for each I we are going to get capital M sample. So for m going from 1 up to capital M. Let's say we are going to sample xim equals xim minus 1 plus epsilon I as theta star of xim minus 1 comma sigma I. So at every point, I take a step which equals the approximate gradient, and then plus square root of twice epsilon I times zim. So zim is essentially a normal distribution I have. And then I said finally, after capital M steps, for the next value of I, so I set I plus 1 0 to be xim. So this is how we do it. So essentially it's this Langevin dynamics. We are essentially we are performing Langevin dynamics with decreasing variances. And here, if you recall, Langevin dynamics consist of adding a gradient term and then adding a Gaussian noise to it. So this is how the annealed Langevin dynamic, this is how it works. So you may now see that this is all happening by adding these ZIs, but this is happening in discrete time, right? So here we are performing a discrete time based sampling. So the question is that can we make it a continuous time based sampling? Okay. So this is how. So this is the main question, and now we use the sort of the Brownian motion theory in order to achieve that. So here we can consider x tilde at multiple sigma i's. So we can consider at multiple sigma i's as xi when x to be normally distributed with mean x and variance sigma I square identity. Okay, so we can model it as a Markov chain. With xi given xi minus 1 to be normally distributed with mean xi minus 1 and variance sigma I square minus sigma I minus 1 square identity. So note that here when we are having this sort of a thing, then essentially the so let's say so basically x it's essentially okay. So let's say x1 is normally distributed with mean x naught, which is x, and variance sigma 1 square I. Okay, so essentially I can write it as x1 as x naught plus sigma 1 times z1. Okay, and where z1 is coming from normal distribution with mean 0 and variance identity, right? Because I've scaled it by sigma 1, the variance changes to sigma 1 square I. Now x2 is given x1 is normally distributed with mean x1 and variance sigma 2 square minus sigma 1 square I. So x2 is essentially x1 plus square root of sigma 2 square minus sigma 1 square times z2. Okay, where z2 is normally distributed with mean 0 and variance identity. And you can check that now I can write x2 as x naught plus sigma 1 z1 plus square root of sigma 2 square minus sigma 1 square z2. So mean of x2 is going to be 0 and variance of x2 is going to be so see this is going to be x naught plus sigma 1 z1 plus square root sigma 2 square minus sigma 1 square z2. So variance of x2 is going to be variance of x naught, which is 0, plus sigma 1 square variance of z1. So this is 1, right? So plus sigma 1 square and then plus sigma 2 square minus sigma 1 square times variance of z2. So this is again 1. And if I add up all these, I'm going to get sigma 2 square, which is what I wanted, right? And mean is going to be again x naught, because the terms which I have added, they have all 0 mean. So essentially x2 is going to satisfy the distribution, right? Whatever I wanted. But now I have cast it as a Markov chain. So I start from x0, then conditioned on x0 I sample x1 with mean x0 and variance sigma 1 square, and then condition on x1 I sample x2 and so on. Okay. So here essentially what we have now is that, let me just rewrite everything we have so far. So we have xi, so x0 is going to be my data x, and xi given xi minus 1 is normally distributed with mean xi minus 1 and variance sigma I square minus sigma I minus 1 square times identity. Right. So basically xi is going to be xi minus 1 plus zi times square root of sigma I square minus sigma I minus 1 square, where zi is coming from normal distribution with mean 0 and covariance identity. So now coming back, right? So how do I model it as a continuous time process? So firstly, from I am going to change to a continuous time t. And now when I say xi is xi minus 1 plus zi times this thing, so I'm going to say x of t plus delta t, right? So I is t plus delta t equals xi minus 1, which is x at t, plus this zi. And now I want a continuous time sort of sampling of random variables. How do I do that? So I already have access to Brownian motion. Now what I do is that, since I want an independent random variable at every time step, so how do I get access to that? So I use that independent increment property of my Brownian motion. So since my independent increments are independent, so let me take this increment w of t plus delta t minus wt. Now this has variance delta t. So what I do is that I divide by square root of delta t, that will give me variance unity, and this is now my sort of replacement for zi. And this thing I'm just going to write it as square root of sigma t plus delta t squared minus sigma t squared, right? I had sigma I square minus sigma I minus 1 square, so I'm going to write it as sigma t square minus, so these are multiplied, right? So this is in the numerator only, this square root of sigma t plus delta t square minus sigma t square, this is in the numerator. Okay, so in fact I can rewrite it. So what we have is x of t plus delta t, this equals x at t plus w at t plus delta t minus wt over square root of delta t, okay, times sigma t plus delta t squared minus sigma t squared. Okay, and yeah, so essentially so this is what we have now. Okay, and now I can write it as delta xt. Okay, so x of t plus delta t minus xt, that I'm going to write it as delta xt equals delta wt over square root of delta t times square root of delta sigma t square. So essentially dx at, as as delta t approaches 0, what we have as dx is dw over d sigma t square by dt, right? So basically d by dt of sigma t square, right? And this is now essentially a differential equation with dw terms, where dw represents the Wiener process. So this is a differential equation with dw terms, so where dw represents Brownian motion. So w is the Brownian motion, which is also called as the Wiener's process. Okay, and here xt, this is actually a differential equation on random variables. So xt is actually a random variable, right? So it's a x as a function of time. Overall it's a stochastic process, and at different instances of time I get different random variables, Okay, and as t increases, as time increases, so does the variance of xt. Right, so this type of differential equation is called a stochastic differential equation. So actually this has a more formal interpretation. We have given more of an informal touch to it. So in order to cover the formal sort of things on stochastic differential equations, we'll have to study stochastic calculus in more depth. So today we are just going to look at it from an informal or intuitive point of view. And so from an intuitive point of view, it looks something like a differential equation, but except that there are these dw terms. So these dw terms, these are essentially my so these terms, they are essentially coming from differential changes in the Wiener process, and this is how the differential equation is designed. So next what we have is, let's try to get a sort of a continuous time variant for DDPMs or deep diffusion probabilistic models. So if you recall the DDPM, so if you look at the forward process, so that consists of x naught coming from a data distribution p data, and xi given xi minus 1 is normally distributed with mean square root alpha I xi minus 1 and variance 1 minus alpha I identity. So we define beta I to be 1 minus alpha I, and now xi given xi minus 1 is normally distributed with mean square root 1 minus beta I xi minus 1 and variance beta I times identity. Right, so here xi is square root of 1 minus beta I xi minus 1 plus square root of beta I times zi. Right, so this is how I had this process. Now let's move to continuous time. So how does this process look in continuous time? So in continuous time, what we have is that I'm going to replace xi by x of t plus delta t. Xi minus 1 is what I'm going to replace by xt. And now this is interesting. So beta I don't replace by beta t, I replace by beta t times delta t. Okay, and you may be wondering why. Okay, because the thing is that so if what I'm going to do over here is that xi is square root of 1 minus beta I xi minus 1 plus root of beta I zi. So if I try to expand it for further steps, then I would get root of 1 minus beta I, root of 1 minus beta I minus 1. Okay. So I would get root of 1 minus beta I, root of 1 minus beta I minus 1, x of I minus 2 plus root of 1 minus beta I square root of beta I minus 1 zi minus 2 plus square root of beta I square root of beta I minus 1 zi minus right. So 1 minus beta is as it is. Xi minus 1 I'm going to expand as 1 minus beta I minus 1 xi minus 2 plus root of beta I minus 1 zi minus 1. Okay, and then plus root of beta I zi. Yeah. So essentially we'll see that what's going to happen is that beta i's are going to be additive over the process, but since i's the intervals of I, they represent intervals of delta t's. So if we have to add them, we'll have to take care of that time intervals also. So essentially beta t delta t, what it ensures is that when I add up these beta i's, I end up integrating over beta t's. So that actually makes sense in continuous time, right? And that's the reason why we need to introduce this delta t term. Okay, and zi as before, we are going to replace by wt wt plus delta t minus wt over root of delta t. And the reason is that we have independent increments, right? And we want to ensure that these zi's are all independent of each other. So this is the only way. Now coming back to the equation. Okay, so this equation. So let's take this equation to continuous time. So what I'm going to get is that x of t plus delta t from xi, which is x of t plus delta t, equals square root of 1 minus beta I xi minus 1. So xi minus 1 is xt, and 1 minus beta I is 1 minus beta t delta t, the square root of this thing. And then plus square root of beta t delta t times what I have is wt by square root delta t. So the square root delta t's, they get cancelled. And this is how the equation now looks. So this is approximately xt times 1 minus of beta t delta t by 2. Okay, and then plus what I have is root beta t times delta wt. So here we are using square root 1 minus x is approximately equal to 1 minus x by 2. So now what I get is that delta x, okay, so if I have x of t plus delta t minus xt, which is delta x, equals minus of beta t xt delta t by 2, okay, plus square root of beta t times delta wt. Okay, now as delta t approaches 0, what we get is dx is minus of beta x beta xt dt by 2 plus root of beta t dwt. Okay, so this is called as the variance preserving stochastic differential equation. Previously what we had was a variance exploding stochastic differential equation. The reasons why it is called as variance exploding stochastic differential equation, because over time the sigma i's were increasing, right, in the discrete process, and in the continuous process also these sigma t's, they are forming some increasing function. This is called as a variance exploding stochastic differential equation. Whereas for DDPM, the differential equation was designed in order to ensure that the variance remains the same. And note that the initial condition in both these differential equations is that in both these stochastic differential equation is that x0 is coming from pxx, which is the distribution of data. But now in order to be able to sample from x0 coming from pxx, what we'll need to do is that we'll need to be able to reverse the differential equation. So that's what we will need to do. Now how do we reverse a differential equation? Reverse the stochastic differential equation. So to do that, we'll take the forward, let's take a most general form of the forward SDE. So the general form was dx equals what we take the general form to be as dx is fxt dt plus dt dw. Okay, so this in general, this is the diffusion process or forward SDE. Now we define ptx as the distribution of xt. So here the reverse of a diffusion process is also a diffusion process, right? So the reverse is given by dx equals fxt minus gt square times gradient x log ptx dt plus gtw bar, where w bar denotes the reverse Wiener process. Now you may be wondering, okay, how have these score functions, how have they come up over here? So the idea is that when we reverse a forward SD, these score functions automatically enter. And this is the most interesting part, right? So here we never started anything about score modeling or anything, right? We just defined a stochastic differential equation, but it turns out that the reverse actually it consists of the gradient of the log probability, which happens to be the score. So in order to be able to generate the reverse sample, we'll automatically have to learn these score functions. So note that the two differential equations which we have seen as continuous approximations to DDPM or noisy conditional score networks, none of these contained the score functions at all, right? So here what we had was dx is minus beta x dt by 2 plus root beta t dwt. This didn't have score function. If you go back and look at the SDE for noisy conditional score networks, this did not have anything about the score function. But when you reverse any of them, you are going to get this score term, and that is why in order to be able to generate samples from any of these two, we'll need to learn the score functions. So need to learn scores. Okay, and that then you will be able to implement the reverse SDE. And note that if your goal is not to generate the whole trajectory in reverse direction, but the goal is only to sample a point from the data, then you can even use this deterministic ODE for the reverse modeling, and you can just write it as dx is fxt minus half of gt square gradient x log ptx dt. So note that this does not have any dw term also now. And the thing about this deterministic ODE is that, so here we can generate samples from marginals, of PTX, right? So basically you'll be able to generate samples from the data, right, if you reverse it for the full time interval capital T, but the trajectory will not have the joint distribution of the trajectories you want. You will only get the marginals at every time step. So in that case you can even use a deterministic ODE. So just read the paper that has full details on experimental comparison of how deterministic ODE performs, how the stochastic reverse SDEs perform. So all that is there. So read that paper for more details. They have lots of other interesting ideas also, which we have not covered in today's lecture. So in the interest of time, so just go ahead and read that. So in the next lecture, I'll try to cover deep diffusion implicit models, and then we'll be able to end this course. So thanks all. Bye.